Hi, my name is Hyunjin Lee from KAIST. Today I will present our work Semi-supervised key point estimation for echocardiography video. Medical ultrasound, particularly echocardiography, plays a critical role in diagnosing and monitoring cardiac disease because it provides real-time imaging. Accurate assessment of left ventricular structure and function is essential for identifying conditions of the heart. However, conventional clinical measurements rely heavily on manual annotation, which is time-consuming and subject to operator variability. Thus, learning-based automated key point detection in POX-view is required for accurate diagnosis. Public datasets such as EchoNet provide around 20,000 static images, but without key point annotations. This means we can train single-frame detector, yet we cannot direct supervise temporal consistency across the video. However, even unlabeled echo videos still contain rich temporal information. So we asked, how can you leverage this unlabeled data to enhance temporal consistency? Recent advances in computer vision, particularly in AR, VR, and robotics, have shown remarkable progress in point tracking. Methods like co-tracker, TAPI-IR, and PIPs effectively model interframe correspondence across videos. Inspired by this, we reinterpret the interframe relationships of cardiac key points as a point tracking problem. This perspective allows us to reverse temporal coherence as a supervisory single, even without dense annotations. Based on this idea, we propose a semi-supervised temporal key point trajectory refinement framework that enhances both spatial precision and temporal stability in POX echo video analysis. This is an overview of our framework. It consists of three main steps. The first step is training a baseline network. We trained a supervised static key point detector based on HRNet, which provides the initial key point prediction for each frame. The next step is confidence-based frame selection. Not all frames are equally reliable, so we leverage the heatmap confidence scores to identify high-quality frames. These selected frames are then used as stable anchors for subsequent tracking. The final step is training our tracking network called EKTNet. Its backbone is built upon an MLP mixer architecture. The network outputs refined key point trajectory across the entire video sequence, improving both temporal consistency and spatial accuracy. Now I will explain the proposed EKTNet in more detail. This figure illustrates the overview structure of our semi-supervised learning strategy. The key challenge here is how can you train on video data without dense labels? To address this, we designed a dual-loss semi-supervised framework that enables learning from unlabeled videos while maintaining temporal consistency. The first loss is the pseudo-optical flow loss. We use a pre-trained optical flow model based on PWCnet to estimate pseudo-motion between frames. This provides coarse but intuitive displacement supervision for the key point trajectory. The second loss is the patch correlation loss. We extract local patches around the predicted key points and minimizing the patchwise MSE between corresponding frames. Importantly, frames that are temporally distant are assigned lower weights. As training progresses, this loss provides a more refined and localized constraint, further stabilizing the key point trajectories. In addition, we adopt an iterative refinement strategy inspired by Raft. Instead of predicting key points in a single step, the model progressively updates them over multiple iterations. For this one, we apply iterative weighted scheduling. Early iteration emphasizes the pseudo-optical flow loss for coarse global alignment, while later iteration focus more on the patch correlation loss for fine local refinement. The next section covers the experimental details. First, regarding the dataset construction, we evaluate our method using acquired POX-view echocardiography video. Our dataset includes 4 key point annotation per frame. This is a sample from our data. It is sample for key point tracking data collected from multiple ultrasound machines, including GE and Philips systems. The acquired dataset includes various cardiac pathologies. Table 2 summarizes the data distribution of the PLOX video dataset. Now let's move on the experimental results. First, the qualitative results. Setting models often suffer from temporal jitter and unstable key point trajectories. In contrast, our proposed method maintains smooth and consistent trajectory across the entire cardiac cycle. Importantly, it accurately tracks clinically meaningful landmarks, which is crucial for reliable functional measurements. Now let's interpret quantitative results. We compared our method with several existing learning-based approaches and conventional tracking methods. Proposed network consistently outperform all of them across evaluation metric. Interestingly, some general computer vision trackers achieve reasonable distance average scores. However, they struggle with biomarker MAE and temporal stability. This highlights an important insight. General point tracking models do not inherently capture structure of cardiac motion. In contrast, our model incorporates anatomical context and echo-specific supervision, which explains the consistent performance improvement. We conducted extensive ablation studies. First, loss configuration. Using only pseudo-optical flow loss provides cross-alignment. However, combining both losses achieves the best performance. This confirms the complementary nature of the proposed losses. Second, semantic feature input. Adding contextual features from a scanenet improves performance. This demonstrates that the embedding anatomical semantics enhances trajectory precision. Third, confidence-based initialization. Selecting the highest confidence frame clearly outperforms both first frame and random initialization. This shows that proper initialization plays a critical role in cardiac motion tracking. Finally, let me present the disease classification result. To evaluate clinical impact, we performed classification on 3 cardiac diseases: heart failure, cardiomyopathy, and myocardial infarction. We extract IVS, LVID, and LVPW measurements across the entire cardiac cycle and trained an SVM classifier using 5-fold cross-validation. As shown in table, proposed network consistently achieved the highest AUC across all 3 diseases. These results indicated that temporal refinement improved disease discrimination. More stable and accurate trajectory leads to more reliable functional biomarker, which directly enhance classification performance. However, performance may be degraded under poor acoustic conditions or myocardial occlusion, highlighting the need for more robust tracking in challenging clinical cases. We anticipate that this neural network can support cardiac function assessment in point-of-care settings where ultrasound image quality may not always be optimal. This is the end of the presentation. Thank you for your attention.